missing the midterm tomorrow?
No, you'll get the midterms back on Thursday. Also, it's been pointed out that I'm behind on my marking for the labs. You'll also get your labs this week. So, I don't have any comments at all on the midterm. I haven't even seen them. I just picked them up this morning from the TA. But they will be back in your hands on Thursday. Just a reminder about the schedule changes. The lecture that got converted into a lab last week will be on November 27th. It's Friday, November 27th. I don't have a room for that yet, but that'll be the date to make up lecture. So, because we've been away for so long, let's just sort of start back with SignalSpace once again. So, when we, at the point of the break, once again, or up to the midterm, basically what we've covered is how to communicate a single binary bit from a transmitter to a receiver. We've figured out how to optimally design the receiver. We've figured out how to analyze that receiver and figure out its probability of error. So the basically everything we do from now on will build on that base. What we were starting to talk about just before the midterm that I'm going to revisit now is basically treating signals as vectors and treating collections of signals as members of a vector space. So this turns out to have some useful mathematical consequences that build on what we've been talking about up to this point. So signal space, and a quick review of what we were talking about. The basic idea is that signals in discrete time are vectors. So in other words, if you have S0 of k, I mean, this is defined, generally it's defined for k equals 1 through n sub b. So therefore this can be written as a vector with elements S01, S02, and so on, S through nb. And so this is a vector. Like so. And similarly, S1 can be thought of as a vector. So a few things that we talked about last time, just reminding you of the of some properties of vectors. So one thing was dot product or inner product. If I have a vector A and B, I have vectors A and B, then A dot B, the sum from I equals 1 to n. Say n is the number of elements in both A and B of AI times BI. There's a rule that two vectors are orthogonal if A dot B equals 0. And the interpretation of A dot B is sort of the projection of A onto B. or vice versa. So in other words, if you want to know what component of A goes in the direction of B, you basically take the dot product. And geometrically, it looks kind of like this. This is A, this is B. There's some sense of, so let's suppose B has length 1. And I want to know what component of A goes in the direction of B. So it turns out that A dot B is equal to norm A, norm B, cosine of the angle between them. And that is exactly this segment right here, if B is equal to 1. Which leads me to remind you about vector norm. Vector norm, which looks like this, the norm of A, let's say, is the sum from I equals 1 to n of AI squared, and then the square root of that sum. Or in other words, it's equal to the square root of A dot A. And in some sense, vector norm basically means the length of the vector. So we left off last time, so this should all be a very quick review, both from last class and from when you took linear algebra, probably in your first year. But where we left off last time was talking about vector spaces and a basis for a vector space. So vector space is basically it's a closed collection of vectors. And what I mean by a closed collection is that if you have two vectors, if A and B are in the vector space, let's call it B, then any linear combination of A and B is also in B. So for instance, alpha A plus beta B is in B for any scalars alpha and beta. So why this is important is because this is how we're going to represent signals this way. When so if you recall back to we were optimizing system design, what we assumed was that any signal that was transmitted would be a scalar multiple of S0. So S1 was a scalar multiple of S0. It turns out that you can represent, if you have two signals that are not linear multiples of each other, you can represent them as a vector space. In other words, you can find two vectors, A and B, so that S0 is a certain linear combination of A and B, and S1 is another linear combination of A and B, and therefore they're both in this vector space. Ultimately, what we're going to do when we express more than one vector in a vector space is we're going to change the design of our receiver as follows. We're going to have a match filter for one component of the vector space, and a different match filter for the other component of the vector space, or as many components as there are. So when we had only one signal and everything was a multiple of that signal, so S1 was a multiple of S0, we only needed one match filter because everything's just a scalar multiple. When we have multiple dimensions, we need multiple match filters, one match to each dimension.